let's get into the big topic of open source, something that we actually say at Red Hat.
We have a
This is so
we
awesome.
are an open culture that believes
It's actually
in
a big
employee
piece
What is that process that a developer, or let's say a
As the
developer-
Kubernetes ecosystem really boomed,
Hello and welcome to this week's Ask an OpenShift Admin Office Hours. I am co-host Andrew Sullivan, joined as always by the other co-host, Mr. Jonny Rickard. How are you today, sir?
I'm good, man. How are you?
I can't complain. I'm in the tower today. You can tell by my lovely television background. The secret is the reason why there's a TV behind me is because the two whiteboards on the other side of this room are actually the flow for this year's Red Hat Summit demo. So I've decided not to spoil that surprise for anybody who's going to be at Summit or watching the live stream. So that way you're pleasantly surprised when you see some of the really amazing and cool things that we've got on stage for you. So
Yeah, that's awesome. That'd be the worst thing. It's like surprising a birthday party or ruining a surprise birthday party. You know, like, yeah. I'm sorry. My bad.
So I can tell you, like I'm looking at this and I've seen it evolve over the last few weeks as we've been working on it and stuff like that. I'm really excited about seeing these things. Summit is going to be exhausting this year for me personally. Like all the stuff that we've got going on. I mean, it was too last year, but all the stuff we've got going on with booth stuff and sessions and labs and the customer briefing center and the executive briefing center, like all of this other stuff. Like Summit is Summit, and there's nothing like it, and it's amazing, and I love it. But man, is it exhausting.
Yeah, this is my first time going, so like I'm really excited. I've never been to it. Like if it's anything like KubeCon, then I can only imagine.
Yeah, KubeCon is KubeCon's a lot of fun as well. I haven't been to a KubeCon since pre-COVID. I think the last one I went to was 2019.
Okay.
I was supposed to go to Amsterdam in 2020, and it got canceled.
Yeah.
So 2019 was the last one I went. Since then, I delegate those things.
Yeah.
And then, the advantages of being a manager sometimes. But yeah.
Yes.
Anyways, welcome to our audience today. Appreciate everybody joining us. So today's topic is one that is near and dear to my heart, and I think is something that most of us as administrators find interesting, and that's sizing. Right? Kind of one of the first questions that we ask ourselves when we start down the path of deploying a cluster or any resource is how much resources do I need? So we recently updated the OpenShift Virtualization Cluster Sizing Guide. And I want to kind of walk through that and talk through some of the scenarios and examples that are inside of there. But even though it's titled as OpenShift Virtualization, really it's a framework for any OpenShift cluster. We can ignore the virtualization part and kind of apply it of how do I identify my workload and then work backwards from there in order to determine what I need. So we'll talk about that here in a few moments. And as always, please don't hesitate to ask any questions here in chat. Reach out to us anytime if you're not watching us live. Excuse me. If you're not watching us live, you can always reach out to us. Both Jonny and I put our email addresses here on the screen: Sully SULLY at redhat.com or Jonny JONNY at redhat.com. We always love to hear from y'all. And answer any questions that we get offline, because we know that the majority of people watch us not live. That being said, we do love our live audience, and thank you all. I see a number of familiar faces, including Christian, who I haven't seen in a while here. So welcome back. And no, Christian, the cluster sizing guide was not the bane of our existence. The subscription guide is the bane of at least my existence.
Yeah.
I do love me some subscription guide. My quarterly penance for, I don't know, some wrong that I have done in a previous life, I guess. With that being said, Jonny, do we have any top of mind stuff today?
No, just the docs migration happened. The firewall changes where they added the host to Quay.io. I believe that's already gone down. Everything else I think is just kind of like spinning up for or towards Summit. And I haven't really heard anything back from the KubeCon EU stuff yet, so nothing really to report yet.
Okay. Yeah, I think the one thing I wanted to mention, there's always 9,000 things going on in the world of OpenShift and the ecosystem and everything else. So I admit that I struggle to keep up with anymore. So the one big thing that I did notice recently, and by recently I mean literally yesterday, is that upgrade paths from 4.17 to 4.18 in the stable channel are now available. So if you were waiting on that to happen, now you can do those upgrades. And this is whenever we talk about these things, I always remind folks that if you want to upgrade kind of as soon as the new release is available, the fast channel is fully supported. So you can, you letting the dog in or out?
I'm letting her in, but she's like, I need more room than what you're giving me. So she's like pushing on the door. And I'm like, dude, what are you doing? But I'm trying to do it without yelling at her.
I was at home yesterday, literally in the middle of a presentation. One of the cats jumped up on my chest. Like, all right, take it down a notch, buddy. You know.
God, I mean, she's just a pain in the butt. Dude. I'm over here, I'm opening the door, and she's just like, more. And so she's a 115-pound Rottweiler, so she's got a little bit of muscle behind her. So
you look very suspicious as you were doing it. You kept looking back at us like.
well, it's because I was making sure I was muted because I'm like, I'm wanting to yell at her, like, dude.
Anyways, what was I saying? Oh, fast track, or the fast channel rather. Fast channel is fully supported. So if you have need to update your clusters, you know, if there's a reason that you want 418 previously, but now, you know, when 419 gets released, right, there's always that 45 to 90 day window where, you know, the stable upgrade paths are not, or upgrade paths are not available in the stable channel, but they're always available in fast, and they're always fully supported in fast. And we did have, the name is escaping me, but we did have that team come on. It's been 2 or 3 years ago. They came onto the stream and talked about like how they make those judgments and how they, you know, basically determine when a path is ready to be added to the stable channel. So really interesting stuff from the engineering team and the release team. So
Yeah, and I can confirm everything that you just said. Like I updated our cluster from 417 using the fast channel, and then updated the stable channel, I think this morning when I think you posted a note and I was like, oh, let me go check. And then so I went out and looked, and it was actually there. I did it because I wanted the latest of MCE. So that way we
oh
can
yeah,
start deploying for that 18 cluster. Stupid
yeah.
dog.
So funny enough, one of the other topics that, so today we're talking about cluster sizing. One of the other topics that we have on the backlog is hosted control planes, and in particular using hosted control planes with OpenShift virtualization. So for Red Hat folks, we had a lab on this at Red Hat 1, whenever Red Hat 1 was, 6 weeks ago or something. So we, you know, the goal is, or my hope is that basically we can show that lab to you all, to the audience, so that way we can let you all know and give you insight into hosted control planes and what that looks like and what it looks like to host OpenShift on OpenShift virtualization. I'm biased, of course. I think it's really cool. So, all right. While I studiously ignore Slack, anything else, Johnny? Should we just get started?
Yeah, let's get started. I do want to say I also love hosted control planes. I think I wish I would have more time or could find more time in the day to mess with OpenShift virtualization. Like I really do want to mess with that whole workflow. So I'm interested in seeing some of those talks and doing some of those labs and stuff like that. But like I use hosted control planes every single day. Like it's got some nuance that pisses me off sometimes, but like by and large, my general like overall experience with it has been awesome. And I do talk about it every chance I get.
I agree. Of especially as it has matured and
Mhm.
become more easily consumable. You know, ACM is not required, right? All you need is MCE, but ACM has a whole provisioning wizard that integrates everything, right? The clusters come online and they immediately have clusterlet, so they register with, you know, the ACM instance. You can push down policy and all of that. Like it's a really powerful solution.
Yeah,
Um,
yeah,
and
it's awesome.
and you can use hosted control planes with OVE. So if you have an OpenShift virtualization engine cluster, you can deploy hosted control planes inside of there. You know, you can use, you know, to basically host all of your virtualized OpenShift on top of that. Although in that model, you would have to use core-based subscriptions for those hosted OpenShift clusters. rhope 9 stable path seems to be open. A caveat if you had multiple networks using OVN. Oh, interesting. Okay. I have not seen any of the or had not gone and looked in depth at any of those release notes. I just saw the release team sent a message out saying that it was available. So thank you
Yeah.
for letting us know that, rhope 9. All right, let's talk about cluster sizing. So the first thing I'm going to do here is I'm going to share a link to, oh, all right. I promise I remember how to use a computer.
Dude, trust me, I I get it.
I hit Command Tab, and so I have two different browser windows, right? And so one is my usual Chrome profile that I'm using
Mhm.
for Restream here, and the other one is my streaming profile. And or Command Tab doesn't switch between those windows; it switches between applications. So I have to use
Oh yeah,
Command tilde, and
Tilda.
tilde is and then anyways, I confused myself because
Yeah.
that happens. So first thing I'm going to do is share this particular link, which is a KCS where we publish the sizing guide. And effectively what I want to do is share my window here. And then I want to kind of walk through this document and look at a bunch of things. As always, please don't hesitate to ask questions as we go through this. I only have one screen today, so I may not see your questions, but I
I'll let you
fully
know.
trust Jonny to interrupt me at any point in time and let us know. That being said, and Pravesh, I see you're asking questions about Dell AI and et cetera. So don't hesitate to ask us questions about other topics as well. So if there are things not related to today's topic that you want to ask about, put those questions in there. We'll do our best to answer them. If we don't know the answer, then we can always follow back up and see if we can. Well, we will follow up internally as soon as we can, and we can always follow up on the stream as well. And I will say that oftentimes this is how we get new stream ideas, new topics for the stream. So let's see. I want to know about Dell AI and a box with OpenShift AI. So I'm not familiar with that solution specifically. I don't know if you're referring to the Dell Apex solution or something else. Ooh, there we go. Now we can be on screen too, Jonny.
Or
So
viewers.
I know. So yeah, I will say that. So one, if you are referring to Dell Apex with OpenShift, I don't know very much about that particular solution. You can reach out to either Jonny or I, send us an email, and I can connect you with some folks that know more about it effectively. So. Wooter, we cannot share ODF between clusters, but FDF. So FDF is Fusion Data Foundation, which is the IBM storage solution. As provider mode, how do you consume this in provider mode, and why can't this be done in ODF? So we'll have to defer to the IBM folks on how to do that. That's another one of those, if you want to send an email, we can connect you with the right folks on the FDF team in order to help with that. As to why it can't be done in ODF, honestly, I don't know the answer to that. I can only assume it was a conscious decision as a result of, maybe it's something that we just don't want to support anymore. Maybe it's something that we didn't see use cases, for that, or I should say widespread use cases. You can always find a use case for something, but enough to justify that support. I'm loath or I'm hesitant to say that it was like, oh, IBM wants to encourage folks to use FDF. I say that I've been at Red Hat since before the IBM acquisition, and I have Jonny, maybe you have a different perspective, but I haven't seen from the OpenShift side where they force us to do things like that, right?
Same.
There's never been we want to limit OpenShift in this way in order to encourage folks to go to IBM for these types of things. They let us be independent in that regard, right? We want to be
Yeah.
the Kubernetes or the OpenShift Switzerland, if you will, and work with everybody on all of the things equally. So
Yeah, the only time I've ever seen anything directly related to IBM is with like Cloud Paks and how they bundle OpenShift stuff together. But like outside of that, yeah, I haven't seen any real impact.
Yeah, but that's on the IBM side. That's
Right,
where
right.
IBM tells their product teams you need to work with OpenShift rather than the other way around.
Yeah, I think it was early on in the acquisition when like there was some sales stuff going on between like our consulting team or sales teams and theirs, and maybe I'm just misremembering, which is very possible. So because I am old.
I mean, I think you're older than I am, so yes, definitely. Yeah, that's the way it works.
It hurts.
All right, so let's talk about cluster sizing. So if you go to this KCS, you will need to have an account with Red Hat. So note that anybody can get an account with Red Hat. You just go to developer.redhat.com. You can register for one, and then you have access to all the things. There is no cost associated with that. So once you have access here, all you need to do is go to this KCS and then click on the attachments down here at the bottom, which will take us to this cluster sizing guide. It is 14 pages of bedtime story if you're having trouble sleeping at night. Let's scroll past all this nonsense and get down here, because what we really care about is the actual act of sizing. So sizing is one of those things where it's like asking somebody, right, how long is a piece of string? Without understanding various characteristics and the things that are important and all of that other stuff, you don't have any way of actually making meaningful or important decisions. So with sizing, we can do it kind of two different directions. And this document approaches it from the direction of, I have a workload and I need to know how much or how to size my cluster in order to accommodate that workload. Now, there's nothing that says that you couldn't do the inverse using this document as well. It would just be a little bit different procedure. And by inverse, what I mean is I have a set of resources. I have a set of servers or virtual machines or whatever, and I need to know how much workload I can host on those. Both of them assume that you have an understanding of what your workload requirements are. So if I have, a set of servers, a set of resources that can host, that have X CPU and Y memory and Z storage, it becomes, okay, well, I have workloads that are A, B, and C size. I can host this many of them in each one of those. I will point out, if you have a already running cluster and you're curious, like, oh, how many more of these pods can I deploy into my cluster? There's already a tool for that. So if we go to docs.redhat.com and I choose OpenShift Container Platform, and then I search within this, and I want the cluster sizing tool. And is that the name that we use it by anymore? Let's see. I promise that there is a tool for this. I'm just struggling to use the new search.
I was trying to remember what it was called. Is it a capacity operator, something like that?
Yeah, maybe that's a cluster capacity. Let's see, cluster capacity.
Nope.
Auto scaling. Nope. I promise it exists. I'm going to roll on and let you search for that in the background, Jonny, because I got you typing away. So there is a tool that you can use inside of the OpenShift cluster. Literally, it's you define, like, here is a pod spec or other resources, and then it runs as a container, and you basically say, tell me how many of these can be deployed into this cluster, and it'll go through and it basically determines exactly that. And it will even spit out, if I remember correctly, at the end, it'll spit out like, oh, you can deploy 312 of these, and the limiting resource becomes memory or something like that. So there are tools for determining how much additional workload a currently running cluster can host. So the other thing that I will note here is that cluster sizing is one of those things where basically we're trying to make an educated guess of what the first version of the cluster needs to look like based off of our workload requirements. So we know that workload always changes, right? We've all been administrators for some period of time. We've all been doing this long enough to know that, like, today my applications team says that they need these resources. Tomorrow the business just decided to acquire, we're purchasing a new application, we need capacity for that, and it can dramatically change things. So the good news is with OpenShift, we can change that cluster geometry at any point in time. Right? We can add and remove nodes non-disruptively, we can resize nodes, we can do all of those things inside of there after initial deployment, and we don't have to really be concerned about getting it right the first time and never being able to change it. So I bring that up specifically because, one, yes, we can change it, but two, we need to know when and by how much to change it. And that's where the monitoring and metrics becomes really, really critically important. Make sure that you're using, by default, when you deploy a cluster, OpenShift metrics is installed and available, right? At a minimum, periodically, maybe once a month or once a quarter or once a year, go and look at that information. Like, what does my overall cluster utilization and resource consumption look like? Is it growing at an accelerated pace? Do I need to plan to add more resources sooner rather than later? So on and so forth. I'll point out that is particularly important with bare metal clusters, where oftentimes our hardware procurement cycles are not rapid, to put it politely.
Yeah.
Right? Virtual clusters are a lot easier, and virtual clusters, there's an argument to be made that you almost don't need to do sizing. You just let the cluster size itself through autoscale, right? So bare metal clusters, right, we pretty much always have to do some sort of sizing exercise to get started. But virtualization or virtualized clusters, I feel like you can play a little more, I don't want to say a little more loose, but you don't have to be as forward thinking when you
There's room for error.
Yeah.
Yeah.
Okay, so getting started, I'm not going to read all of this to you. Kind of one of the important things here. So yes, we need to know the size of our workloads. We need to know or the size of the workload independently and the number of each of those that we want to deploy. And then we need to know things like overhead. So for standard containerized workloads, the overhead is typically going to be negligible unless you're running things like sidecars, right? Stuff like that. Service mesh adds some overhead for each one of the pods that's deployed. You'll find in the documentation each one of those is there. So like this, remember this guide was written for virtualization, OpenShift virtualization. So like each virtual machine has a set of overhead associated with it, and that calculation is right here in the documentation, right? So for every virtual machine that gets deployed, right, here is how we determine the amount of overhead memory it's going to consume that we need to factor into our capacity calculations. And the same thing for CPU down here, right? So at the cluster level, the things that are running, the operators and other things that are actually implementing OpenShift virtualization consume these types of overhead. And then on a per VM basis, there is some, well, maybe not with CPU, but with memory, there's a little bit of overhead as well. Oh, I didn't realize that was going to open that in the same window. Okay. So overhead is, and this is discussed later on. So there is also overhead associated with the cluster itself. This right here is referring to specific to the workload if there's any overhead associated with it. So I don't remember which step it is, but there is one that accounts for like capacity that we need for kubelet and for the other cluster functions like logging and monitoring and so on and so forth. So last but not least, overcommitment. So this is really, we highlight it with OpenShift virtualization and VMs, but really it's important with any cluster that you're sizing. Because even if it's a virtual cluster, I'm deploying on top of vSphere or something like that, that underlying hypervisor is almost certainly overcommitted as well. And so even if you do no overcommitment inside of OpenShift, at the hypervisor level, it's probably being overcommitted. And we need to at least be aware of that and the impact that it's having to our clusters. My personal opinion, and overcommitment is always a decision of risk, right? What is the risk that the performance impact of overcommitment causes more impact to the business than the cost of not overcommitting, if that makes sense. So you need to be aware of that overcommitment level, whether you're overcommitting in OpenShift or you're overcommitting at the level underneath OpenShift, and how that's going to impact. My personal preference is to not overcommit at the hypervisor level. So if it's a virtual OpenShift cluster, don't overcommit at the hypervisor level. And the rationale for that is because OpenShift is, one, already by default going to be overcommitting things, and two, it's a concentrator of applications. Just like virtualization is a concentrator of servers, right? Pre-virtualization days, we would have a rack of servers that was, it was 42 U's, so 42 servers. Today, in that same 42U rack, I might have tens of thousands of virtual machines running inside of there. So the impact of losing a single rack in my data center now has significantly different characteristics than it would have 2 decades ago. The same thing with OpenShift. Right? Maybe it's still virtual machines, but before it was deployed across 2 or 3 or 400 virtual machines, all of these different applications. And now it's deployed across a couple of dozen virtual machines inside of my OpenShift cluster because everything's containerized and running in Kubernetes. So we want to be careful with those resources, and we want to allow the scheduler and the resource assignment to happen as close to the application as possible. So because that's Kubernetes, that's OpenShift, we want OpenShift to be the ultimate decision maker and who does and doesn't get resources, rather than something underneath OpenShift that it has no visibility and no awareness of. So anyways, long-winded way of saying, please be careful, please be cautious. And as always, monitoring is critically important. I've been running my mouth for a few minutes, Jonny. Am I missing anything in chat, etc.?
Nope. I think you're good. RHope 9 posted some stuff for ODF and external mode, and Wooder was like, "Yeah, I get it." So they want info on how to make up that centralized cluster.
Got it. So I started off, when we wrote this, we assume that the workload is not characterized. So what I mean by characterized here is I understand exactly what my application or my virtual machine requirements are, and therefore I can apply that data directly against any new deployment. I think reality is that, one, we don't know what that is oftentimes. Even for deployed applications, it can be hard to determine based on how good our monitoring and metrics and other tools are. And two, it's always changing, right? We're always getting new applications that need to be deployed. We're always having new things spin up, right? All that type of stuff. So understanding, basically how many of this shape of thing can I host is really important. And so in this particular guide, we created these sort of t-shirt size things based off of anecdotal experience, as well as some data that we collected from various customers. In order to make, at least for again, this is OpenShift virtualization centric, this document is, so to make an estimate of the size of virtual machines that we would expect to host. So using that data as a starting point, we can figure out, I need infrastructure that can host, so many small, medium, large, extra large types of virtual machines. And that is more or less what we do as we go through the rest of this particular document. So let's start with step one, which is just raw capacity required for the workloads. And that is exactly as I described above, how many of each of these workload types or workload shapes do I want to be able to host inside of my cluster? Importantly, because this is OpenShift virtualization and we need to account for that memory and mostly for memory with virtual machines overhead, we include that at this level as well. So you can see with a cluster that I want to host this many virtual machines in, I need, which comes to a sum of 1,700 virtual machines, right? I need to have the ability to host 8,000 vCPUs and approximately 36 terabytes of memory, plus the overhead. So the way that when this was written, the way that we kind of genericized things was to create the average virtual machine. Because at the macro level, right, the average is really what matters, right? It's the average is the easiest way for us to determine the overall capacity and the ability to host things. Because more than likely, your workload breakdown is not going to be precisely like this. You might end up with 300 extra large and 10 large and 1,000 mediums and no smalls, right? So you can't say I'm always going to have this precise breakdown. Instead, we're just going to go with the average VM and work from there inside of here. So you can see the average VM is just shy of 5 CPUs and just over 22 gigabytes of memory. So step 2 is overcommitment. So overcommitment is it is very, very common, but often not well understood. So at risk of derailing us and tangenting here for a little bit, I will keep us, or I will try and start by being a little bit narrow, but please don't hesitate to speak up and ask questions. So OpenShift doesn't implement any hard overcommitment, CPU overcommit limits or ceiling. Right? When you think about overcommitment, it is I have X amount of CPU, right? 1, 2, 5, 32, whatever CPUs in my node, right? Be it physical or virtual. I have a finite amount of CPU. When I schedule a workload to that node, it is going to consume some amount of that CPU. And overcommitment is basically I am going to say I want to put 64 or 128 CPUs worth of workload onto this 32 CPU server because I'm going to assume that the majority of the time, if not all of the time, my workload is not going to consume the full amount of CPU inside of there. So the correct overcommitment ratio is probably never going to be known, right? Or let me rephrase that. The correct overcommitment ratio is going to be entirely dependent on your applications, and it is probably going to change over time as your applications are doing various different things and your application makeup changes over time. So any time that I have more than 2 processes running on my server, I'm overcommitting, right? Because without a limit or without something in place to prevent a single process from consuming all of the CPU resources on my server, then that process can consume all of those CPU resources. And by its very nature, if there is a second process that can also consume all of those CPU resources, well, now I'm overcommitted. So can you control that? Yes, within Kubernetes, we have, or OpenShift, we have limits, right? A limit is placed on a pod, and that limit will, at the kernel level, it will prevent it from consuming more resources than it has been assigned. I'll point out with CPU in particular, limits can have unintended consequences. So what I mean by that is when I create a limit for my virtual machine or for my Kubernetes workload, doesn't matter if it's a virtual machine or not. Let's say that I give it a limit of 1/2 of a CPU. Right? And so what that means is that in any given, in the Linux kernel, which uses CFS, completely fair scheduler, for any given scheduling interval, which is 100 milliseconds, it can access up to 50%, 50 milliseconds of that CPU time. So if I have an application that needs 500 milliseconds of CPU time for it to accomplish what it needs to do, if it had no limit, it would effectively be able to accomplish that in one cycle, right? In one scheduling cycle. It would consume the entire cycle and then it would be done. But because it's limited, it breaks it up into different segments. So even if the CPU is sitting idle for the other 50% of the time, that workload has been limited to just that much within that scheduling interval. So this is one of the reasons why limits in particular are often considered, I'll say risky, or at least we should be very careful with implementing them because there may be unintended consequences there. Yeah, and there's been many, if you go on the internet and search with your favorite, search engine of choice or your, LLM of choice and ask about it, you will find multitudes, volumes of information about this. Internal folks who have seen me publish about this on like the email list and stuff, I often refer to it as religion.
Yeah,
Right?
it's Nomen Kitty, right? I mean, it's
yeah, like we're starting to see what is effectively, either religion or somebody called it, what do they call it? Cargo cult behavior around whether or not to use requests and limits for the applications.
Yeah.
Of like, hey, I've always done it this way and it works, so I'm just going to keep doing that, even though we may not know what's going on. That's the cargo cult aspect. The religion is like, oh no, you will never ever use a limit, but you should always use a request, or the inverse.
Hmm.
One thing I wanted to point out while I'm on the topic of limits. So this is my OpenShift 418 cluster. If I come down here to compute and nodes, and I look at my nodes, I don't remember if it's in the YAML output or if I need to do an actual. Yeah, so when you, let me see if it comes up. Make you larger. OC get node. See describe node. Oops, describe node. So yeah, so like down here, right, when I describe my node, it'll tell me these allocated resources. And I'll have like CPU and memory and stuff like that. And I think that out of the box, there is a Prometheus alert or an alert manager alert when the limits exceed the available resources on the node. My personal opinion, and of course everybody should make their own, determine what it is and what it means and develop their own opinion about it. My personal opinion is we can probably ignore those, because what that is the sum of all limits on the node. So my node has, say, 16 CPUs, and I have deployed 32 pods, and each one has a 1 CPU limit. So therefore, by the limits calculation, I am oversubscribed by 2 to 1. But reality is, again, it's oversubscription. Most of those pods are not going to consume all one CPU all of the time. So the limits is less important, in my personal opinion, when it comes to an overcommitment ratio and stuff like that. So, but definitely, make your own determination on that one. Circling back around after my little 5-minute sidetrack there on overcommitment and what it means for CPU. So with OpenShift, by default, there is no overcommitment limit that is configured across the cluster. Right? Typically, what my recommendation is use the monitoring and determine, like, hey, my nodes are starting to run out of capacity. I need to add more nodes. And then we let the scheduler do what the scheduler does, and it sends workload out to nodes that have available resources. This is also where cluster autoscaling comes in, really importantly, of like, cluster autoscaling will take effect when a workload cannot be scheduled due to resource constraints. Right? There's not enough resources for it to schedule, so therefore it requests basically more nodes from the underlying infrastructure, and then the cluster scales up and it can host it. So OpenShift virtualization is a little bit different. OpenShift virtualization has an overcommitment limit of 10 to 1. And the way that is implemented is with a CPU request for each virtual machine. So if I come over here to my cluster and I look at I'm going to switch over to the virtualization view here. By the way, if you haven't seen OpenShift virtualization in a while, there's been some pretty awesome changes inside of here. So like, I now have this dedicated virtualization console in my cluster that shows me all of it limits all of the noise here on the left-hand side for things that I don't care about as a virtual admin. If I come in here to the virtual machines view, you see I have this lovely tree view that shows me all of my virtual machines in each one of the namespaces and stuff. So you see, in case you can't tell, I did a webinar recently and used this cluster for it. So
Nice.
anyways, if I look at this particular virtual machine, and then I go to the pod that is hosting that, and I look at its configuration, the way that is implemented is with a resource request. So somewhere down in here, nope, that's too far down. Anyways, I don't see it, but I promise it's in here. Here we go, request CPU 100M. So for every CPU that is assigned to the virtual machine, the running virtual machine will have a CPU request in the cluster for 1/10 or 100 millicPUs. And that's how we enforce that 10 to 1 overcommitment inside of OpenShift virtualization. So just keep that in mind. 10 to 1, most FIRT admins think is a relatively high number. Anecdotally, when I talk to folks, it's usually 2 or 4 to 1. So let's talk about memory overcommitment for a moment. So memory overcommitment in Kubernetes for a long time has been interesting, shall we say. And by interesting, I mean there is no overcommitment, right? When a node, CPU is considered a compressible resource. If CPU comes under contention, then the kernel just throttles the processes that are asking for CPU, right? It says you have to wait until there's available time, so it just slows down that process. With memory is not compressible. So effectively, when the node runs out of memory, there's nothing else that it can do. Right? It can't, eject pages from memory for the application because that can cause a whole host of other issues. Because Kubernetes, like I don't know how long anybody else has been doing Kubernetes, right? Step one when you deploy Kubernetes to the node is turn off swap.
Yeah.
So the operating system can't kick pages out of active memory and down into swap because swap didn't exist. So what we saw and what we see is the out of memory kill process take action. The node the memory is full, it needs to recover some memory, so out of memory kill kicks in and it identifies low priority pods. And by low priority, I mean ones that literally have low priority assignment to them, or are a part of the burstable. No, not burstable. What's the QoS class below burstable? I don't remember.
Don't get me lying.
Anyways, it will basically begin to terminate pods in order to free up memory resources on the host. And then, Kubernetes cloud native applications, the expectation is, the scheduler will see that pod was terminated and we'll just reschedule it somewhere else inside of the cluster. For virtual machines, that's bad, right? We don't want virtual machines to be arbitrarily and unexpectedly basically have the power plug pulled out from underneath them, right? That's how we end up with OS corruption and bad things. So the OpenShift virtualization engineering team worked and continues to work with the upstream Kubernetes community to reintroduce native Kubernetes swap capabilities. But the first step is something that we lovingly refer to as WASP. So if I come over here and I search for WASP, and let's see, we'll go here. Virtualization, placement rules, hyperconverged, nope. Here we go. Configuring higher VM workload density. So WASP is the tool that's used to provide swap specifically and only for virtual machines. So effectively, if you're running OpenShift virtualization, you have WASP configured inside of the cluster. It'll go through and it will turn on swap for those VM processes, and then it will, as they encounter, as the host memory consumption reaches a certain point, it will begin to swap those virtual machines out. And then it can eventually lead to those virtual machines being live migrated away, so long as they have sustained swap activity inside of there. Because sometimes we see processes start up and they consume a whole bunch of memory, and then it triggers a little bit of swapping, and then the memory consumption shrinks down and it never swaps again. We don't want to have arbitrary and unnecessary live migrations. So we avoid that by waiting for it to do short-term sustained. You can actually define those parameters down here somewhere. Here we go. In the swap agent on the nodes, like how long and how much swapping there needs to be before it will start to trigger workload to move around. So overcommitment with memory with virtual OpenShift virtualization is a thing we need to be aware of, right? We make sure to implement that and do it using WASP agent. The decision to do that or not, again, is one of risk to the business and how much that impact of swapping has on, and the impact of performance for our virtual machines is versus the cost of not overcommitting those resources is. Note that this starts with OpenShift 4.17. So if you're using OpenShift virtualization pre 4.17, we just don't overcommit memory with OpenShift virtualization. Let's see. So I'm switching back over to look at chat for a moment.
Yeah, it's all good. All clear.
Okay.
Our Hope9 made a point about the people that complain about limits are the ones that are using most of their requests.
Oh, I see you found the switching back over here. I see you sent me the link for the cluster capacity tool.
Yeah, I think that's what you're looking for.
Yeah, OpenShift cluster capacity tool. I wonder why I put in OpenShift cluster capacity tool, didn't I? Or cluster capacity tool? I wonder why it didn't show up.
Yeah,
Anyways,
it's tucked in under the scalability and performance stuff.
got it. Anyways, yeah, I mean, we can see here, right? Here I'm defining a application or a workload type and the things that are inside of here. And basically down here, I say, how many of those can I run? And it says, oh, well, the pod requirements are this amount of resources. And using that information, each one of your nodes can run this many instances inside of there. And then the reason why it will eventually be unable to, right, 88 instances total, and it'll end up being unschedulable due to insufficient CPU. So super helpful tool, and you can use that with any workload inside of there.
Yep.
Where was that? So factor in overcommitment in CPU. Very, very important. When we created this guide, we were walking through, and if you read through this, we're using an example. So we assume a CPU overcommitment ratio of 4:1 and 2:1 memory overcommitment. Because this is OpenShift virtualization, again, we pulled that from anecdotal evidence as well as kind of what we've seen interacting with customers. So we feel that those are safe values, but safe is always relative and subjective. So as always, be sure to use the values that are appropriate for you and your applications. So where we went, and at the end of all of that exercise, right? So we started off with an average VM that is 4.7 CPUs and 22 gigabytes of memory. So basically we divide those values by the overcommitment ratios. So the result is the average virtual machine after overcommitment is now actually 1.2 CPUs and 11 gigabytes of memory that we need to use for capacity estimation. So from here, we want to start to identify potential node sizes that we want to use in our cluster. And this is based off of a few different factors that can affect the overall cluster architecture. So one is density. Basically, how dense do I want my workload to be on each one of my nodes? So we can see here, right, OpenShift as of, I think it was 4.12 or 4.14, supports up to 2,500 pods per node. However, generally speaking, there are caveats associated with that, where 2,500 is probably not the ceiling that you want to aim for. I would say, and again, this guide is OpenShift virtualization. So in particular, we want to use probably something like 500 or even 250 virtual machines per node, just out of sheer, and I talk, it's later in this document, I'll talk about it, out of sheer like failure domain protection, right? 500 VMs is a lot of resources to lose. Even if I have, 50,000 VMs in my environment, that's like, 1%, right? Is that right? Yeah. Losing 1% of all of my resources might be pretty significant, especially if it's the wrong 1%. 50,000 VMs is a huge environment, right? So we just want to be cognizant of how much density there is and how that impacts, in particular, failure. So if we assume, right, we want to use up to no more than 500 VMs per node here, right, we can do the simple math of dividing that by our total VM count by that 500 number, and we end up with needing a minimum of 4 nodes in order to host that. Is 4 nodes the right number? Maybe, maybe not. Again, failure domain and just overall resource density. There's some math later on that talks about like how big those nodes need to be. Is it more cost effective to have 4 extremely large nodes? You see here 510 cores and over almost 5 terabytes of memory, versus having 8 or 12 or 16 nodes that are going to be fractionally smaller than that. 2 is hyperthreading or SMT, depending on which CPU vendor you're using. So how do I factor that into my capacity calculations? So if you're doing OpenShift, virtual OpenShift, your virtualization administrator has already factored this in. If you're doing virtual OpenShift virtualization, this is something that you want to factor in, which is a hyperthread does not have the same performance as a real core or a real thread running inside of the cluster, or excuse me, on the CPU. So again, anecdotally, what we see, you see a common choice is to treat the additional thread as providing a capacity of half a core each. So on a CPU that has 64 cores and 128 threads, right, this would result in the capacity being 96 cores from a capacity calculation treatment. So this can be a little bit confusing in some ways because you'll say, oh, I have this many threads, or I have this much. The scheduler will think that there are this much resources, but we want to be careful with that because, again, those are not quote unquote real threads when it comes to capacity purposes. There's a note here saying that we're going to assume that this has already been accounted for. So what that means is in this document, like down below, when we talk about, we're using 96 core CPUs, that could be implemented as a 64 core, a server with a single 64 core 128 thread CPU, or a server that has two 32 core 64 thread CPUs, so on and so forth, or let's divide it again, four 16 core 32 thread CPUs, so on and so forth. Yep, this is just kind of highlighting exactly what I laid out above. So resource isolation. So this is one where the goal is to understand how to balance the CPU and memory ratios to avoid stranding resources. So what this means is, let's say that my virtual machines, right, I deploy every one of my virtual machines has 4 CPUs and 16 gigabytes of RAM, right, a 4-to-1 memory to CPU ratio. If I purchase servers that have, I'm going to make up numbers here, 16 CPUs and 1 terabyte of memory, where now my CPU or my memory to CPU ratio is like 64-to-1. I don't know if that's what it actually is. I made that up off the top of my head. I don't think that's right, but like it's way out of whack. What's going to happen is I'm going to consume all of my CPU resources, right? 16 cores, so 4 virtual machines. And now I'm going to have all of these memory resources that I just can't use, right? Because each of my virtual machines was only 16 gigabytes of memory. 4 of them is 64 gigabytes of memory. My server has a terabyte of memory. So there's 900 and something gigabytes of memory that I just can't use because there's no CPU available. So we're isolating those resources. So the goal of this whole section here is basically to point out, like, hey, factor that in when you're sizing your hardware. So that way you don't end up in situations where my CPU or my memory resources are exhausted. I can't allocate anymore, but the other one, I have resources that are available, but just not able to be used. So node overhead, right? This is the resources that are needed on a per node basis in order to basically have the cluster or excuse me, the node function. So there is, let's see if this will open. Oh, it did open a new tab. So this is inside of OpenShift, there is a feature that will automatically reserve some resources based off of the size of the node. So if I look at this down here, right, machine config pool, and then I come down here and turn on this, where did it go? If I turn on, all right, come on. Where's the actual setting? You're just telling me how to, well, it's just telling me how to configure a machine config pool. Here we go, auto sizing reserved. So if we set this auto sizing reserved to true in my machine config pool, it will automatically set the kubelet values to reserve resources for its functionality. How much those values, how much CPU and memory it reserves is based off of a known calculation. And that calculation is over here. So basically what happens when you turn that on is it executes this script on the node. So if we look inside of here, and there's a version of this for each version of OpenShift. So this is the 4.17 version, but I haven't noticed it really changing. Anyways, it will run through this bash script, right? Function dynamic memory sizing, where it will go through, you feed it a value, and it tells you how much memory is going to be used based off of, or reserved based off of that value. And then it echoes that out, it sends that out, which gets appended into the kubelet config inside of your node. So I don't have, you can, if you so choose, copy this function out and have it basically feed it information. So copy this function out, paste it into your bash prompt, and then execute the function. I don't have a command prompt that's easily shareable at the moment. And you can get those values ahead of time. But, so definitely something to, if kubelet can't get the resources it needs to function, then that's sort of an issue for multiple different ways. I always recommend that you, at a minimum, set this value. So it won't change unless you change the resources inside of the cluster. But you can set this value by default, so that way all the nodes get some resources reserved. And then again, relying on monitoring, if you realize that that's too much or even not enough, it's very possibly not enough, you can then go in and manually set those to more appropriate values. So I skipped over a step up here in the previous step. So basically we made some assumptions that and started evaluating some potential cluster, or excuse me, node sizes. So let's say we want to go with 192 cores, right? In that case, how many virtual machines does that result? And if that is using that number, 160 virtual machines, how much memory would we need? So the end result is a server that has 192 CPU cores, and because we rounded up because 1792 is not an even number in base 2, we went with 2048 gigabytes of memory. So with those numbers, now we can figure out that, okay, I need a cluster with 160 VMs per node. I need 11 servers to host my 1700 virtual machines. So when we get down here, where we're saying, all right, our cluster is 11 servers of 192 cores and 2 terabytes of memory, when we've used those numbers and, when we use those numbers and plug them into these node overhead, is there enough resources available in the spare capacity, because we rounded up on the previous numbers, that we don't need to add additional nodes? And it turns out that we do, but just barely on the CPU front. So node overhead does not affect our server count in this instance. If I were to, adjust these node sizes and node counts, it could potentially affect that overall. And there's down at the very bottom of this document, we have a table that shows different calculations. So last but not least, in this particular section, next one is step 4, is the failure domain. I talked about this before. Basically, from a business perspective, making a judgment based off of the risk of losing any 1 or 2 or however many servers and the impact that would have to the applications. So you see here, for a cluster with 11 nodes, a single node failing represents 9% of total capacity and or 160 virtual machines that need to be restarted. So is that too much? Is that not enough? Am I okay accepting that? Am I okay accepting more? Do I, so on and so forth. And that can affect our cluster node size as well, or excuse me, our node size as well.
We got a couple questions, Sully, if you want to.
Yeah, go for it.
So the first one is more of a statement. It's from Gamal, and I'm sorry if I butchered your name. He says that he had sent you a question about your article on LinkedIn. So just so you know, you have a message waiting for you. And then Dwayne asks,
I'll admit you, and I will interrupt you and admit that I am terrible at social media, so apologies.
No, trust me, I totally get it. And then Dwayne asked, how much is a server with 192 cores? Is there like a hardware list? And my response back to that is like it varies on vendor. Like some vendor, because it's feature driven and CPU architecture driven and features within the architecture and stuff like that. So I mean, it literally can go from you can buy a really cheap CPU to like a holy crap, I just sold the farm to get this one kind of architecture.
So from a hardware list perspective, there actually is one. And it is the RHEL hardware list. So RHEL hardware catalog. So if I look for the RHEL Red Hat certified hardware, and if I come down here to system and I click explore, and then basically what I want, so each version of OpenShift uses RCOS, Red Hat Enterprise Linux Core OS. As the name implies, Red Hat Enterprise Linux, it is based off of RHEL. The specific version of RHEL changes with periodically based on the version of OpenShift. Core OS RHEL versions. Sorry, I'm searching in my other window because I think I have the link already.
Yeah, and my bad. I think I may have read his question very literally
No,
instead of.
Yeah, you're good. So this KCS, as soon as it loads, maps which version of OpenShift you're using to which version of RHEL you're using via RCOS. So you can see if I deploy OpenShift 4.18 or 17 or 16, I'm actually using RHEL 9.4. And so the RHEL 9.4 hardware list is the one that I need in order to basically determine which physical servers are supported or not. So note that these servers are certified by our partners. So Red Hat didn't go and acquire some HPE Alletra storage server 4140s and test them. HPE tested their servers with RHEL, and then they verified that it works as expected. So this HCL is what we use in order to determine support. I'm just going to click on one of these at random. We'll go with I've never heard of this brand before. So I'm an Axial AX300 Edge server. So if we click on this and we click on the certifications tab, you can see that it's certified with Red Hat Enterprise Linux 9.5 and later. So note that OpenShift is today 9.4 based. So that means that OpenShift would not be supported on this particular piece of hardware. Right, if I click back and I look for, let's come down the list a little bit. Let's pick on this Supermicro server. So for this one, you can see 9.4 and later is certified, but this one also has an OpenShift an OpenShift item here. So why do some of these have OpenShift and some of them don't? Basically, so far as I have been told and assured, is if Red Hat Enterprise Linux, whatever version for your RCOS is on this list, you are supported. What this means is that this hardware vendor, when they tested their platform, went the extra step of testing IPI with their server, specifically IPI. So what this means is that you can expect that OpenShift bare metal IPI will work on this particular server inside of there. Some of them also have a Red Hat OpenShift virtualization item here as well. When that exists, that means that this hardware vendor also deployed OpenShift virtualization to the node and was able to deploy at least one virtual machine to it. So if this OpenShift container platform doesn't exist, that doesn't mean that your server or that OpenShift is not supported on that server. If the OpenShift virtualization one doesn't exist, as it doesn't on this particular server, that doesn't mean that OpenShift virtualization is not supported on the server. It just means it wasn't explicitly tested on that server. Still supported, just not explicitly tested. The only one that is important from a support standpoint is this one. This just gives you additional assurances that like IPI will work and stuff like that. Hopefully that answered the question, and maybe a little more.
Yeah. And we also have one more question from Kamal. Will the auto size reservation include sizing for computing resources needed for internal monitoring and logging components and the worker master infra node role?
No, the auto size only accounts for kubelet resources. So actually, I think it might be, yeah. So it's either the step 4 or step 5. I don't remember which one. One of these steps basically talks about exactly that, of like that auto size thing only accounts for kubelet resources that are reserved for it to function. If you're deploying, monitoring, if you're deploying logging, if you're deploying a registry, if you're deploying all the other things inside of that cluster, those are separate sizing exercises. Note the same is also true of control plane resources. So it doesn't reserve resources for the control plane. Some control plane functions do have resource requests associated with them so that they have protected access to resources. Some don't. However, all of the control plane pods, as well as all of the node pods, so things that are providing low-level functionality for the node. So let's go to and nodes, and if I pick on my node here and look at the pods, right, there's a ton of stuff in here like this bridge marker and cloud credential operator and like all of these things. Their priority is going to be higher than generic workload pods. So if you start to come under resource contention, the pods that are providing like core node functionality are going to are going to be last on the list for termination by like out of memory kill and stuff like that. Let's see. So next step, so adjusting for the cluster architecture. So what this section is really referring to is like, how am I going to lay out the nodes inside of my cluster? So at a minimum, right, there's control plane architecture, and I don't think we did a good job in this section of laying out that there's also infrastructure nodes that we need to account for, or infrastructure workload that we need to account for. So there wasn't a lot of work because this is very, very specific to you and your cluster and your workload and your business, and your risk tolerance. We didn't put a lot of effort into this section of like going through all of the nuances and creating a fully fleshed out sizing example here. But instead, we made sure to incorporate like various questions and various things that you want to account for. So how many control planes are we going to use, right? 3 is the standard. However, for 5 node control plane, right, that's going to be some additional capacity that's used. Note that yes, 5 node. So 1, 3, 4, and 5 node control planes are supported with bare metal clusters. Andrew's personal opinion is 3 control plane nodes with a bare metal cluster should still be the default. But you may want to consider a 5 node control plane depending on how long it takes you to replace nodes. So what I mean by that is with a virtual cluster, right, I have a control plane node that fails, it goes corrupt, something happens to it. It probably takes anywhere from a few minutes to a couple hours to provision a new VM and replace that control plane node. So not really a big deal, right? A small window, small period of time where the control plane is quote unquote at risk, where if another node were to fail, then the control plane would go read only because etcd lost quorum. With hardware, typically it's more like days to weeks before we can replace a failed node. So we have to ask ourselves, okay, if it's going to take me 2 weeks to replace a failed node, do I have enough other capacity in the cluster where I can reassign an existing compute node to become a compute and control plane node? Or do I need to plan from the beginning of being able to tolerate more failures? And it's going to take me 2 weeks to replace that node. During that time, I'm not going to do anything else with the control plane, but it's still 4 nodes, so I can still survive another node failure. So again, considerations to take into account and how that affects, overall cluster size, resource requirements, etc. Here we talked about the infra qualified workload, stuff like that. Do I want to have dedicated infrastructure nodes versus infrastructure workload just scheduled as regular workloads? Do I have control plane nodes that are both control plane and infra, but not schedulable for regular workload? Right. All of these cluster architecture things factor into how much capacity I need for the overall cluster. So I think down here we determined, so for the sake of simplicity, we're just going to say that all of those things, control plane workloads, infra workload, et cetera, are going to use this much resources. So we just added that in. And when we add that in, you see that there was enough excess capacity amongst the existing cluster members, the existing 11 nodes and whatever we had sized them at above, that we didn't have to add more. Step 5, so adjust for high availability resource contention. So high availability is the amount of resources that we need to recover pods, recover workload in the event of a failed cluster member. So the way to think about this, and I think down here makes the most sense, right? So I have a 10 node cluster that is hosting, 100 pods, virtual machines, whatever, at 80% utilization. So if each node represents 100 units of workload, then 10 nodes can host 800 units of capacity. And 80% utilization means 800 of those 1,000 are being used. So if I have a cluster node fail, that means that the overall, so I now have 9 nodes in my cluster, and the overall capacity is now only 900 units of capacity. But I still want to be able to schedule 800 units of capacity of workload to my cluster. So therefore, my cluster, my overall capacity now went up to 89% of 9 nodes instead of 80% of 10 nodes. So for every node that I want to account for the failure capacity, I have to reduce the amount of used capacity that I'm using in my cluster. So if I have, you know, and we walk through it down here, right? A 10 node cluster that is running at 90% capacity, so 900 of 1,000 units of capacity are being used, then we can't tolerate even a single node failing. Because if I reduce the node count to 9, so therefore 900 units of capacity, right, it would be completely maxed out.
Mm-hmm.
So just important factors to account for. You can see we did a little bit of math down here of like, for as I reduce each one of my nodes, what does that mean, and how much capacity that I need to limit myself to in order to account for that recovery capacity, that failover capacity. So
Hey,
we're
Andrew,
yeah, go ahead.
just time warning, time check for you. It's 12:15. I know you got a hard stop, so I just want to make sure that you don't,
Thank you.
that you're aware of it. And then we
Thank
also have a question from Gamal about the resource automated resources, dynamic host or node stuff.
Mhm.
So namespace quotas must be configured for the monitoring and logging for reserving compute resources. Because the previous question was about using the configuration to dynamically, outside of the kubelet.
Was that a question or a statement?
I think he was asking a question. Like, is that statement true that namespace quotas is what must be configured for the monitoring and logging?
No. For reserving compute resources, no.
Mhm.
So quota is not a resource reservation. The way that we do resource reservations is by assigning requests to the pods. So either the pod administrator, pod user can do that. So when I go and define my pod, I go in and create, spec dot blah, 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 whatever, right, requests, and I put that value in there. Or you can automatically have it assigned using a request limit. So over here and go Kubernetes, sorry, not a request limit, limit range.
Yeah.
So a limit range basically says in the absence of existing values for the limits and the requests, use these. And it walks you through like, here's the spec.limits.default. So if nothing exists, create a default limit of 500 CPU and 500, and a default request of 500 and a max of 1 and blah, blah, blah. And you can see how that works out. If it's below that, it will bump it up above it. If it's above that, it will pull it back down. And if none of it exists, then it will put in whatever the default values are. So limit ranges are the way that we enforce those if nobody is putting them manually or willingly. Hopefully that answered the question. But yeah, quotas we don't need in order for that to work. Quotas are more like Jonny is only allowed to have 32 CPUs worth of resources. And quotas, in order for a quota to be effective, then the workload does need to have requests associated with it. So typically what you'll see is when you implement a quota, you also implement a limit range to put at minimum a request in place.
I think we did it. I think we did a stream on this. I feel like it's been 100
Yeah,
years at this
it's been a
point.
while, but yeah, I
Yeah.
think we did. Yeah, so you can see this one continues. So avoid resource contention scenarios such as out of memory, right, where we end up with things being either swapped or OOM killed. So this is where we talk about things like soft eviction. So within Kubernetes and therefore OpenShift, we have, they're called eviction pressure triggers. Eviction trigger Kubernetes. So eviction. node pressure. Yeah, here we go. Eviction signals and thresholds. Right. So basically what this means is that there are two values. One is the soft and one is the hard value. So if I configure a soft eviction threshold for the memory available, it says when the memory level, the available memory drops below this amount, kindly ask pods to terminate in order to free resources. The hard limit is I am going to hard out of memory terminate the pods if my memory utilization gets above this level. So importantly, you can see that the eviction signals are available memory. You can see from the node file system available. So node file system is typically going to be the root file system. Image FS is going to be where varlib containers is mounted at. Sometimes these are the same, sometimes these are different. Oh, actually, there's a third one now. Sorry, image FS is where it will pull containers to. Container FS is where the layers are created at. With OpenShift and CoreOS, I believe both of these are varlib containers, if I remember
Yeah, I think so.
correctly. But you'll notice that this is both capacity available as well as inodes. Importantly, very importantly, you'll notice that CPU is not an eviction threshold. Remember, it's a compressible resource. So I can, if I way oversubscribe my CPU and CPU is pegged at 100%, and there's a whole bunch of processes that are just sitting around spending 90% of their time, waiting on CPU time, that will not trigger any workload to be, evicted and therefore rescheduled to nodes that have lower CPU utilization. The way to do that is the descheduler, and the descheduler profile for doing that, at least with virtual machines, I think it works with other workload as well, is in tech preview right now. Let me see if I can find that link real quick. Here we go. This is an interesting one. Let's see, find this window. Let's paste the link in here. And then I'm going to paste the link in here. So the load aware rebalancing, as soon as the blog loads here, basically does exactly what I just described. It uses the descheduler to look at real utilization on the nodes and then trigger workload to move around. So if we come down here, and is that the right one? Maybe that's not the right one. No, that is the right one. I thought that there was some different graphics on there. Maybe it's down here. Ah, here we go. This is what I was looking for. I didn't scroll down far enough. So let me blow this image up. You can see that that's not the one I want. This is the one I want. So you can see what's happening here is like there's some nodes that are really overutilized and it's causing latency issues and stuff like that. And so we turn on this load aware rebalancing, and effectively it triggers the nodes to basically it removes nodes that are approaching the threshold from eligibility for scheduling and then starts evicting workload. So that way we end up with a place where hopefully our workload is balanced across all of them. There's another example down here of what it looks like. So see this node pressure CPU waiting seconds. So this is tech preview. You can absolutely use this in your cluster today. Normal tech preview caveats apply. In order to enable this, you have to set a kernel parameter on your nodes to surface up the pressure metrics. So you can see this node pressure CPU, like that metric is not reported by the kernel by default. So you have to turn that on first and then it'll be surfaced up and then you can take advantage of it. I don't want to speak for the product management team, but I know they're looking at GAing that hopefully soon. Anyways, long story short, overcommitment and avoiding resource contention is important and something that we want to account for. The goal of this section of the sizing guide is basically determining what are our eviction thresholds, because we don't want to schedule, we don't want to put workload that goes up to that maximum. So if my eviction threshold is 4% of capacity, that means that I can only schedule 96% of my total node capacity. And then if I also add in the previously discussed node failover capacity, then I need to also deduct that. So in this instance, the result is that my nodes can only be scheduled for maximum utilization of 78%. So now, instead of my nodes being 100% scheduled and I only need 11 nodes in my cluster, if they're only 78% utilized, scheduled, then I actually need 14 nodes, well, 14.1 nodes in my cluster, and we have to round that up to 15 because you can't purchase just 1/10 of a node. So step 6 is, this is another one where we didn't go into details here because everybody's situation is unique, right? You need to take into account the resources that are required for ODF or Portworx or FDF, right? All these other things. If you have applications that are using things like a lot of SDN traffic, right? So my nodes only have 10 gigabit networking and I have this application that consumes 9 gigabits of traffic. That means that I'm going to have to be cognizant of the capacity in other ways, more than just CPU and memory, and take that into account. And you can account for these things using the special resource operator, where you can define capacity associated with those things and use it when scheduling. GPUs and SRIOV devices are another one. Hey, I have this AI workload. It needs access to a GPU. How do I factor all of those resources in? So, down here at the bottom, we kind of cop out of this and basically say, like, yes, you have to account for these things. Don't forget about it. But because it can get complex and because each one of those is a different facet in the overall geometry, it was one of those that we just stepped back from.
Yeah, safe.
Yeah. Disaster recovery is similar, right? Disaster recovery is one of those, like, when, like, either is this cluster acting as a recipient for disaster recovery workload, or I am sizing a disaster recovery cluster, in which case you have to ask yourself really tough questions like, what's my actual critical workload? Like, what needs to be recovered first, and what is the capacity of that? And then kind of size the cluster according to that. I realize I'm kind of going fast through these last two steps because, like, I don't really know what to say about these, because everything is so, I'll say, snowflakey,
Hmm.
depending on what your workload is and what your requirements are. So last but not least, when we get down to the bottom here is like, hey, we should have like a full cluster. Like I should be ready to identify my cluster geometry and my node geometry from here. So you can see the final step, is a 15 node cluster that is comprised of nodes that have 192 cores and 2048 gigabytes of memory. And again, we mentioned way up in the overcommitment section of, like, this 192 cores could come from, a server that has one socket of 128 core, 256 thread, or two sockets that are 64, 128, so on and so forth. And then we also did the math of, like, how does this change with different sized nodes, right? So 15 nodes of this size, but what if I wanted to have, for whatever reason, this node size is not optimal for me. Maybe that means I can't get this in a 1U pizza box server. I need to have, and all of my servers need to be 1U. So I need to reduce down to 48 cores. So you would need, in that case, 43 nodes. Maybe you want to have a 3-node failure toleration in that instance. So it's 43 nodes required for the workload. So just if I only scheduled my applications, remember that was the 1700 VMs with however much CPU and memory, I would need this number of nodes. I want to be able to tolerate 3 of those nodes failing. And because these nodes are a little smaller, I don't want to, I want eviction to start happening at the 90% level. And so the result is I now have a 52 node cluster instead of a 15 node cluster. And of course, that has other implications as well, right? Larger clusters, have larger meaning more node count, have their own set of implications from a management perspective and everything else. So anyways, I know I honestly didn't expect this to take an hour and 15 minutes to go through, but it's an interesting topic. And again, it's one of those things that we all sit down at some point and kind of start with okay, I need to do this, figure out what I need and what it looks like and stuff like that. And as I said at the beginning, like, you can use this same formula, just kind of in reverse, to work out how much more workload can my cluster hold, or I have a cluster that is this size, how much workload can it hold?
Yeah, this is crazy comprehensive. Like, I was not expecting it to be this deep. This is awesome.
Yeah. So I don't know if we have any other questions in the last couple of minutes here. No. Thank you for
Oh,
fielding all the questions in chat, Jonny. And I see
yeah,
you've been busy in there.
trying to. At least trying to keep up with R Hope 9 and Kamal.
Yeah. I hope, yeah, as long as it isn't feature gate, I'm happy. Some of them are feature gates. You have to be careful with the tech preview ones because I recently had a question come across my desk, which was, so my customer accidentally, they did not realize that turning on the tech preview no upgrade feature gate meant that their cluster could not be upgraded ever again. Can we please reverse this? And the response from engineering and support was, no, it's a one-way street. Sorry. So with that being said, thank you all. I appreciate all of your time and attention today. Hopefully this was helpful, interesting at least. If you have any questions about it, if there's any clarification that we can provide, please don't hesitate to reach out. Again, if you're not watching live, our emails are on screen, or if you're listening to us, I know a lot of people listen to us like a podcast. Sully, SULLY at redhat.com, or Jonny, JONNY at redhat.com. And we are happy to hear from you. And to the point earlier, I am legitimately awful at social media, so please
Yes.
don't rely on social media as a way to reach out to me. Email is by far preferred. If you are on the Kubernetes Slack, is it slack.kubernetes.com or kubernetes.slack.com? Both Jonny and I are there. You can find us on there. You can, if you at us, that'll pop up in my interface. So usually we'll respond within a day or two, depending on how long it takes for the alert to make it to us. Any Prometheus alarms you could share for virtualization for resource prediction? That's a good question. I don't know. I don't know the answer to that one.
Yeah, me either.
Now I kind of, 15 years ago, I actually wrote a series of, way back when I learned, Perl was still a thing, and I remember how to use Perl. I wrote a series of scripts that would do like linear algebra based off of capacity calculations, and for our storage systems. And then I discovered RRD graphs, and that got a whole lot easier. So suddenly it wasn't querying databases and doing a whole bunch of manual work in code. So, but yeah, I can ask about that, rhope9, and see if our team has anything to say about it. I will say that ACM does a phenomenal job of collecting, aggregating, and then sort of summarizing metrics. The way that I've been describing it lately is like ACM federates metrics from across the clusters. So let's pick on virtualization for a moment. You can look at the VM pod or the VM host and get real-time metrics on the performance statistics. You can look at Prometheus for the virtual machine in either directly or through the performance graphs and get semi-real-time information. I don't remember the Prometheus polling interval. I think it's like 15 seconds. And it keeps those and summarizes them up into 1, 5, 15, 60-minute intervals. And it keeps those for, I don't remember what it is, let's call it a month. ACM basically pulls that up and can do summaries at the day, week, month level, and will keep that for years. So you can get this sort of end-to-end idea of what the resource consumption looks like. All right, I gotta go to a kickoff meeting. So thank you everybody for joining us today. Really appreciate your time and your attention. Again, don't hesitate to reach out to us at any point in time. We love hearing from y'all. And we will be back next week, right, Jonny?
Next week, we got
Awesome.
HashiCorp with Rosemary.
Awesome. Looking forward to that one. So thank you all. We will see you next week, same time, same channel. Don't hesitate to reach out in the meantime. Any last thoughts, Jonny?
No, great topic today, Andrew. Yeah, thanks for running this one down. Yeah, I really appreciate it. So, awesome stuff. Thank you.
Yes, sir. Bye now.
Later.